As I said, there's more moving parts in our model of the cosmos. There are more things that do not remain fixed on the celestial sphere and just rotate with it, but yet rise and set, so are off the Earth. And the next most conspicuous one after the sun is our moon. Like the sun, the moon moves along the celestial sphere. It's not fixed. For the same reason, the moon orbits the Earth. It orbits the Earth in the same sense that the Earth orbits the sun, and in the same sense that therefore the sun appears to orbit the Earth, moving towards the east along the celestial sphere. But the moon orbits the Earth much faster. The moon completes a complete orbit around the Earth in what is called a sidereal month, which is 27 and a third days. That means that its right ascension increases by 48 minutes per day. Compare this to the sun's measly 4 minutes. In other words, the moon takes a month to orbit the Earth, the sun takes a year to orbit the Earth. A month is a twelfth of a year, 4 minutes is a twelfth of 48. The mathematics adds up. Now, as the moon orbits the Earth, it also rotates about its axis. We'll discuss next week why this is, but this means that we are always seeing the same side of the moon as it rotates around us. There's the same side of the moon that faces us. This means that while there is no such thing as the dark side of the moon, there certainly is such a thing as the far side of the moon. There are parts of the moon that are never visible from Earth, and those were first seen or indirectly seen by human eyes when the Soviet Luna spacecraft first orbited the moon. So this is why when we look up at the moon, every time we see it, it has this familiar look. We're always seeing the same side of the moon. Now, the moon, therefore, moves to the east along the celestial sphere by 48 minutes a day. The sun moves to the east along the celestial sphere by 4 minutes a day, which means the moon moves faster to the east along the celestial sphere. The moon moves 44 minutes per day farther than the sun does, which means moonrise relative to sunrise is delayed by 44 minutes a day. Because the moon and the sun are in this race, it takes the moon a little bit longer to complete a full rotation of the celestial sphere relative to the sun, to come to the same relative position as the sun. That takes what is called a synodic month, which is about 29 and a half days. This is the time, say, from the moon being in alignment with the sun, and then the moon running ahead of the sun and catching up with the sun 29 and a half days later. As usual, this takes a little bit longer than the 27 days that it takes the moon to complete a sidereal rotation, for the same reason that a solar day is longer than a sidereal day, the difference being more significant here because we're talking about a month rather than a day. Now, the position of the moon relative to the sun controls two things. One is when during the day it rises and sets. If the moon is at the same right ascension as the sun, then it rises at sunrise and sets at sunset because it's in the same direction in the sky as the sun is. Whereas if the moon, say, is 12 hours away from the sun, it's 180 degrees away in right ascension, the moon will rise at sunset and set at sunrise. So rising and setting times of the moon change throughout the synodic month. And in addition to this, of course, the moon's appearance in the sky changes. It goes through phases, and the best way to see this is the following interesting simulation. The best way to understand how the moon's position relative to the sun gives us the phases of the moon is to just do it. And to just do it, you need a source of light. You can use a light bulb, or if you prefer, you can just use the sun. Just go outside if you can't find a light bulb. Anything round. I have a white styrofoam ball here to play the role of the moon, and your head to play the role of Earth. The view from your eyes will give you the view as seen by people on that side of Earth facing the moon of what the moon looks like, and then you simply turn around to perform a complete lunation. To give you a sense of what this looks like, in case you're not going to do it yourself, though I strongly recommend it, what we have here is on the left side of the screen, you'll see a setup in the studio of me holding a moon and turning around in the relative configuration, whereas on the right side, you'll see the image of a GoPro camera that's mounted to the moon, so it shows you the image of the moon as I see it. When the demonstration begins, the moon is in between the sun and the earth. It's on the line between sun and earth, and so the illuminated side of the moon, as we can see in this beautiful picture, faces the sun and therefore faces away from the earth. I see the dark side of the moon, and the moon will be nearly invisible. As I turn to my left, to the east, slowly the western side of the moon will become illuminated, and we'll see a growing crescent until after I've turned 90 degrees, we'll see a waxing quarter moon. Since the moon is now 6 hours or 90 degrees to the east of the sun, it will rise 6 hours after the sun. In other words, the waxing quarter moon rises about at noon and sets about at midnight. As I continue to turn the east, the illuminated part of the moon will grow and become gibbous until at last, when I'm 12 hours away from the sun, I will see a full round moon illuminated. We're going to have to switch cameras at some point to give you the full view because of studio limitations. Don't get confused by that. 12 hours to the east of the sun, the full moon rises at sunset and sets at sunrise, and so the full moon is the only moon that is really up all night and only during the night. You'll note that to give us a view of the full moon, I had to tilt the moon's orbit. I'm holding it way above my head. We'll get back to that in a second. As I continue to turn to the east, now the western part of the moon is losing the sunlight. I see the eastern part of the moon illuminated. It is a waning gibbous moon, and when I reach 90 degrees to the sun again, I have a waning quarter moon. The waning quarter moon, which is 6 hours to the west of the sun, will therefore rise 6 hours before the sun. In other words, rise about at midnight, set about noon. This is the moon we see in the morning. Finally, as I continue turning to the east, the moon becomes closer to the sun in the sky. Only the eastern edge of the moon is illuminated. I find a waning crescent moon, and after a full synodic orbit is passed, the moon is back in line with the sun, and again I see only the dark side of the moon, and we're back to new moon. So, what I hope you saw, and I do encourage you to do it yourself, it's really fun, and you can show it to your friends and family, is that over the course of a synodic month, as the moon orbits the earth relative to the sun, the shape of the visible part of the moon changes in the sky, as well as, because of the relative position of moon and sun, the rise time. So the new moon, when the sun and the moon are roughly at the same right ascension and the moon is completely dark in the sky, rises at sunrise and sets at sunset. The waxing quarter moon, when the moon is about 6 hours of right ascension to the east of the sun, rises 6 hours after the sun. So the waxing quarter moon rises at noon and sets around midnight and is visible all afternoon. The full moon, where the moon is 12 hours of right ascension ahead of the sun, in other words, on opposite side of the sky, the full moon is the only time that the moon rises at sunset and sets at sunrise. And the waning quarter moon, where the moon is 6 hours to the west of the sun, or 18 hours to the east, the moon being 6 hours to the west of the sun, rises 6 hours before the sun, in other words, rises about at midnight and sets about at noon, and the waning moon is visible all morning. So when you see the moon in the daytime, you should not be surprised, but should you ever see a full moon at noon, something has gone terribly wrong. So both the phases and the periodic change in moon rise and set times are completely understood in terms of this model where the moon reflects sunlight and what we see depends on the angle between the moon, the sun, and the earth. You can simulate this. You can go to the simulation page of the University of Nebraska-Lincoln and get a less three-dimensional version. But I encourage you to construct, take a light bulb and a ball of some sort and make yourself a moon. So this describes the moon's motion and the changes in the phase. You noticed that at new moon and at full moon, I had to sort of adjust the moon. I was orbiting the moon about my head, not in a horizontal orbit, but in a tilted orbit, so that it went below the sun at new moon and way high above the sun at full moon. So this brings up the question of what is the moon's declination? Indeed, the moon roughly orbits the earth along the ecliptic, but it deviates from the ecliptic by 5 degrees. For comparison, the sun and the moon are about the same size in the sky, and both of them are about half a degree, so that the moon is distant from the sun by up to 10 times their radius, and so typically the moon passes well below or above the sun when it's, for example, a new moon. And so we have these two circles now, the ecliptic and the orbit of the moon around the Earth. The tilt between them is 5 degrees. The analog of the equinoxes, the hinges at which these two circles are hinged, is now called the nodes, and the line connecting them, the line of nodes. And so the moon is at most 5 degrees away from the sun, which means, among other things, that as the sun moves north and south along the ecliptic, by 23.5 degrees in the summer north and 23.5 degrees south in the northern winter, the moon, which is at most 5 degrees away from the sun, pretty much follows the ecliptic. So the moon, too, is higher in the sky in the summer and lower in the sky in the winter. But it generically is not exactly the same as the sun. It is only at exactly the same declination of the sun when it is along the line of nodes, just as the sun is on the celestial equator at the equinoxes. So twice in each of its rotations about the Earth, the moon lies along the line of nodes. And in that case, the Earth, the sun, and the moon are in the same plane. Interesting things happen, of course, when the moon is in the line of nodes and it is either full or new. Let's see what happens then. In our first lunation, I carefully kept the moon way north, or up in this image, from the sun when it was full, and way south of the sun when it was new. What we're going to do now is see what happens to the full moon when the line of nodes is aligned with the direction to the sun. In other words, the moon, when it is 12 hours away in right ascension from the sun, is at exactly the sun's declination. And we start our demonstration with the waxing gibbous moon, and it waxes until it is becoming full. And then what we see is that from the eastern side of the moon, a fuzzy shadow covers the surface of the moon. Of course, this is the shadow of my head. It would not be as shaggy were it the real Earth, but this is exactly the geometry for a total lunar eclipse. The moon enters the shadow from the west moving east, and therefore it moves out of the shadow, starting with its eastern edge first. So when you see a lunar eclipse take place and then the moon uncover, you're literally watching the moon orbit around the Earth. About 2 weeks later, or 2 weeks earlier, the moon is now at the sun's right ascension. We're getting a new moon, and the moon is still at the same declination as the sun, and we'll see what happens. We pick up the story with a waning crescent moon. The moon moves in front of the sun. When it is at the sun's right ascension and declination, the moon in fact is obscuring the sun. And remember, we're on the daytime side of the Earth. This is midday because it's a new moon. We shouldn't be able to see it at all. In fact, we don't. But then we don't see the sun either. We get complete darkness in the middle of the day. And as the moon continues to move to the east, we see this weird glow on the moon. This is an artifact of a shiny GoPro camera, but even this is instructive. The lens of the camera is still eclipsed, but the bits of the camera on the right-hand side are already shining in the light, and there you can see the reflection of that off the moon. This is what would happen if people living a few thousand kilometers to the west of you erected a huge shiny tower on Earth. During a total solar eclipse, you might see the reflections from that shiny tower on the surface of the moon, and then as the moon continues to move east, the sun is again revealed and it's bright midday. What did the model show us? Well, the moon's orbit is tilted 5 degrees with respect to the sun's orbit, the ecliptic, and so there are 2 points along the moon's orbit at which it is on the ecliptic. Now, as the sun orbits the Earth, or the Earth orbits the sun, there are going to be 2 times a year where the direction of this line of nodes coincides with the direction to the sun, because the sun makes a complete circle, and at 2 antipodal points along the circle, it coincides with the line of nodes. This gives us twice during an average year something called an eclipse season. And the alignment need not be absolutely perfect, because neither the sun nor the moon are point-like objects, but there are 2 sort of 1.5 month periods during each year, and in those 1.5 month period, eclipses may occur. May occur, that is, when the moon is either full or new, so that it is at the correct part of its orbit, at the right ascension, either of the sun or opposite that of the sun, and now at the right declination. So twice a year we have an eclipse season, and during an eclipse season you have usually between 2 or 3 eclipses, one of one kind and flanking it 2 weeks on either side, 2 of the other kind. So you could have a solar eclipse flanked by 2 lunar eclipses, or a lunar eclipse flanked by 2 solar eclipses. By the time the next eclipse of either type would have occurred, the next new moon, for example, the sun is now too far from the line of nodes, and you no longer get an eclipse. So typically no more than 3 per season. And this should happen twice per year. In fact, like everything else that is tilted, the line of nodes wobbles. In other words, the tilt between the moon's orbit and the ecliptic is always 5 degrees, but its orientation wobbles, and as is the case with the Earth, it actually wobbles to the west because it is orbiting to the east. And so the tilt precesses to the west very slowly, once every 18.6 years or so. And this just means that the eclipse year, the year during which 2 eclipse seasons happen, is a little bit shorter than the full orbital year of the Earth, only 346.6 days. And so during each of those 2 eclipse seasons, a new or full moon might lead to a solar or lunar eclipse. A new moon during eclipse season means the moon is in front of the sun and at the right declination, so you can have a solar eclipse. A full moon means the Earth is between the moon and the sun, and the Earth's shadow will obscure the moon, just as my shaggy head obscured the moon in our model. Now, we need to get a handle on the relative sizes and distances of things to understand the difference of the 2 phenomena. So, the moon and the sun are almost precisely the same size, in angular terms, in the sky. If you think about it, the sun is much larger than the moon. From our small angle approximation, we know that it is much farther. The ratio of their sizes is almost precisely the ratio of their distances, so that both the moon and the sun appear in the sky to be about the same size. An interesting coincidence. What this allows is when you have perfect alignment during new moon, the moon is able to completely obscure the sun when you superpose 2 disks of the exact same size in the sky. But this requires perfect alignment, so perfect that in fact it will only obtain for a small region on Earth. If you move a little bit away from that region on Earth, then the alignment is no longer perfect. The alignment is only perfect at one point on Earth, and when I say one point, I mean a region on Earth whose size is up to about 250 kilometers. That's a very small part of a planet with a radius of 6,400 kilometers. And in that region, where the moon's shadow completely obscures the sun, you get what is called a total eclipse. And we have here a beautiful time series of a total eclipse. Notice that as time progresses in this, the moon seems to obscure the sun from the left, whereas in my, and then leave the sun to the right, whereas in my model this was happening the other way around. The reason is that this eclipse in 2001 was observed near Zimbabwe, and near Zimbabwe you're in the southern hemisphere, which means east and west are still the same, but looking, since the sun is now to your north, the moon entering the sun from the west, moving to the east, is now from the left to the right. So a nod to our southern hemisphere viewers. This time it makes sense to you. The moon is coming from the west to the east across the surface of the sun. It obscures the sun completely for a few minutes and then is seen to move away. And what we're watching again is the moon orbiting the Earth, although also this place, Zimbabwe, is being moved along the surface of the Earth by the Earth's west to east rotation and moves out of the shadow, as we'll see in a moment. And noteworthy, when the moon completely obscures the sun, a region around the sun that appeared completely dark before is suddenly seen to be brilliantly luminous. This is called the corona, the crown of the sun. It is not visible when we see the sun itself, or the sun's disk, because the sun's disk is so bright that it blinds us to the brilliance of the corona. But once you obscure the sun's disk, you can see that the region around the sun's disk is illuminated. When we talk about the sun, we'll try to understand what this glowing crown is and how to observe it away from eclipses. A more common phenomenon than this beautiful totality is that when the new moon occurs, the line of notice is not exactly aligned with the sun, and so the moon is a little bit south or a little bit north of the sun, and then the moon would have passed below or above the sun, above it if it were south, since we're in the southern hemisphere, and below if north, or the other way in the northern hemisphere. And then you will find a partial eclipse where not the full surface of the sun is obscured, but only some fraction thereof. And this is far more common because it requires a less sensitive alignment. To give you a sense of what the shadow of the moon on the Earth looks like, here's a beautiful image taken from the Mir spacecraft on August 11th, 1999. And this is an image of Earth, and what we're seeing on Earth is the moon's shadow. So the moon's shadow, as I said, obscures the moon can obscure the entire sun in this inner circle of radius about 250 kilometers. Away, we see this partial shadow. These are regions where if you look up, you can see part of the sun, but some fraction of the sun is obscured by the moon. You can see around it a little bit, and so this is called the penumbra, or partial shadow. People here see a total eclipse. People here see a partial eclipse. And now remember that underneath this shadow, the Earth is rotating, so that this shadow is effectively moving along the Earth at some 1,000 kilometers per hour, and so each individual location only gets a short period of totality. Now, this is what happens if alignment is perfect and if the moon and the sun are indeed exactly the same size in the sky. How can they change? Does the moon shrink? No, but the moon's orbit around the Earth is not completely circular. The moon is sometimes a little closer to Earth and sometimes a little farther. When complete alignment occurs and the moon is on the farther part of its orbit, it's just a bit farther from Earth. Since its size didn't change, its apparent size in the sky is a little bit smaller. It's then smaller than the sun in the sky, and we get what is called an annular eclipse, because you see an annulus of sun, a ring of sun surrounding the moon. This shadow here is the moon. We see some of the corona and even some of the chromosphere around the sun, but what we also see here is a little bit of the disk of the sun, the photosphere as it's called, and the moon not completely obscuring it in this beautiful image of an annular solar eclipse. This is what happens when alignment during eclipse season occurs at new moon. During full moon, what happens is that the Earth's shadow prevents sunlight from hitting the moon, and the moon becomes dark. The moon, as I said, is moving to the east. It enters Earth's shadow from the west. Again, the eclipse can be total or partial, and depending on the quality of the alignment. And we can get a penumbral eclipse when the moon is only in partial shadow. In other words, where from the moon you can see some part of the sun, but some of the sunlight is blocked by the Earth, just as pieces of the Earth were in partial moon shadow. Then the moon just slightly dims. It's kind of hard to even notice it. But when you get a total eclipse, when some part of the moon's surface is completely obscured from the sun, then this is the beautiful image you see. Now this image should surprise you. I mean, perhaps some sunlight is reaching over here. Maybe I didn't time this photo to precise totality. But where is the light coming from that allows us to see the moon, this side of the moon at all? This side of the moon is in fact in total Earth shadow. You cannot see the sun from this area of the moon. What you can see in the sky is a bright glowing Earth. Remember, the Earth is bigger than the moon, so it handily obscures the sun. It's much easier to arrange a total lunar eclipse than a total solar eclipse. And also, a lunar eclipse, when it occurs, is visible, since the moon is dark, to anybody on Earth who can see the moon. So whenever it occurs during your nighttime, you can see the moon eclipsed. It's a far less delicate arrangement than the solar eclipse, which only blocks out the sun for a small fraction of the Earth. But this source of this red illumination of the moon, the answer is here on the slide, comes from light diffracting through Earth's atmosphere. why light diffracting through the Earth's atmosphere would give the moon this famous wine red color is something we'll have to investigate. This is a picture actually taken at our observatory in the solstice eclipse of December 2010. And so this is a pretty image, and lunar eclipses are easier to find and observe. I encourage you to enjoy them. A few more fun facts about the moon while we're discussing the moon. So, two well-known things that people appear to observe. One is that when you see the moon rising or setting, it's near the horizon, it appears larger. This, it turns out, is a psychological illusion. Taking pictures of the moon with a camera, you can measure its angular size. And in fact, if anything, then strange optical effects make it appear a little bit smaller in the sky near the horizon. But there are various psychological theories near the comparison to other objects nearby, angular corrections. I'm not an expert on the psychology, but it does appear to us that the rising full moon seems huge when it's on the horizon and small when it's high in the sky, but this is completely in our heads. On the other hand, there's this other famous illusion which is called seeing the old moon in the new moon's arms, which is that when you see a crescent moon where only a fraction of the moon is illuminated, then you can sometimes imagine to yourself that your mind completes the full disk of the moon, and you can see the part of the moon that is not illuminated by sunlight. And this one is a physical effect. Here's a camera capturing it. Here's the illuminated side of the moon, so the sun is down that way. This side of the moon is dark, sunlight cannot reach it, and yet I see it. So there's some light hitting it, and the reason, of course, is that when the moon is a crescent, if you were on the moon, set up the configuration in your head, you would see that there would be a full Earth in the sky, and viewing the full Earth in the lunar sky means that there is bright Earth light illuminating the moon. So the light that is hitting the moon, by which we are seeing this moon, is Earth light. In other words, light that was emitted by the sun, reflected by the Earth, hit the moon, reflected off the moon, and came into the aperture of this camera. So the fact that you can see the dark part of the moon when the moon is a crescent is not psychological, it is true. You can only see this when the moon is a crescent, basically because once the moon becomes too bright, it blinds us, it dazzles us, and we can't see this. Also, the larger the illuminated part of the moon, the less of the face of the Earth is illuminated. Of course, when we have a full moon, then people on the moon would see a new Earth. The phases are complementary. And so, for both of those reasons, we only see this when the moon is a crescent. So we've made some progress in understanding astronomical phenomena and the way they change periodically. We've got the sun, we've got the moon. Let us close this discussion with some interesting relations between astronomy and timekeeping. I told you that units of time kept being defined in terms of the Earth's rotation and its orbit. This is not a coincidence. We want our time to match what's going on. We want 6 a.m. on our clock to be solar sunrise because that's the time we go out and plant things, work in our fields. And so our 24-hour days are adjusted to be the mean solar day. Our months, the 12 months into which we traditionally divide the year, are approximately lunar. The synodic lunar month is 29 and a half days. Our months are a bit longer than that, and this allows for the rare phenomenon of 2 full moons falling in the same month, which is what colloquially is called a blue moon. It's a rare phenomenon. It requires a full moon right at the beginning of the month, but it does happen. Our definition of a year is designed to match the orbit. A year is 365 days. The Earth orbits the Sun once every 365.2564 days, a little over a quarter of a day. This is a sidereal orbit. In other words, this is the time that it takes the Earth to return to the same position in the sky relative to the Sun, or the time it takes the Sun to return to the same position in our sky relative to the stars, hence a sidereal orbit. The first thing we observe is that the year is not, unfortunately, an integral number of days. This is a problem. It means that since our days turn over every 24 hours, that every 4 years, your timekeeping, if you have a 365-day year, then every 4 years you are off by a day relative to the Earth's orbit. So who cares? Well, accumulate those days for 180 intervals of 4 years, and now you are off by 180 days, which is half a year, which means that now January corresponds to northern summer. This is very inconvenient if you're trying to plan agriculture. And we have a solution to this, right? This was discovered by Julius Caesar, or in his time, and it was his legislation that added leap years. Once every 4 years, we add another day, making that year 366 days long. The average year is now 365 and a quarter days long, and now we never drift more than a day off from having our orbit match our calendar. However, this is not completely precise enough. In fact, what we want our calendar to match is the seasons. The seasons have to do with the relation between the Earth's position relative to the sun, and not the stars, but the direction of the tilt of the celestial North Pole, or the terrestrial North Pole. And remember that wobbles to the west rather than to the east. So a complete rotation where between solstice and solstice, or equinox and equinox, is a little bit shorter than the sidereal year rather than longer. This is called the tropical orbit. The mean time between solstice and solstice is 365.2422 days. Remember that the precession is very slow, takes 26,000 years, so it's not a big effect over a year, but it does make the mean tropical year a bit shorter than 365 and a quarter days. This was understood in the 16th century and led to the correction from the Julian to the Gregorian calendar. Correcting for the deviation between 0.2422 and 0.25 required removing some of the leap years. That is why on centuries that are not millennia, in other words, years whose number divides 100 but not 1,000, we do not add a leap year. We do not add a 29th day to February. Those years are only 365 days long. The average year is a little bit less than 365 and a quarter days long. In fact, it's close enough to this number on average that it'll be millennia before we have to make another correction. And so we definitely use astronomical phenomena to adjust our clocks and our calendars, not for any silly reason, but because astronomical phenomena govern our life, and we need our timekeeping to match that. It's quite an elaborate universe we're starting to build around us. We have the celestial sphere where the stars are fixed. We have a solar sphere that rotates relative to the celestial sphere about this tilted axis so that the sun can move along the ecliptic. We have a lunar sphere tilted relative to the ecliptic around which the moon moves a little bit faster. Moreover, all of these tilted trajectories are also wobbling to the west, one very slowly every 26,000 years. The moon's a little bit faster every 18.6 years. This is very elaborate, but it does explain everything we see, the alternations of day and night, the phases of the moon, eclipses, seasons, almost everything. Let's go to Athens and see what we might have been missing. We're back to our favorite picture of the sky in Athens, and I've allowed the software to show us the ecliptic, and we see the 23.5 degree tilt relative to the celestial equator. We see the intersection of the ecliptic and the equator here at the prime meridian in Pisces. We still live in the age of Pisces. And we see that the part of the ecliptic that's visible at night is mostly the part north of the equator. That's reasonable because end of November, the sun is well south of the equator. The part of the ecliptic that lies south of the equator is what we see during the day. So far, so good. The other thing you'll notice, and I'm sure if you tried to run your own simulation, and certainly if you went outdoors, you will have realized by now that I fudged. I suppressed some things in the simulations I've been showing. In particular, the two brightest objects in the sky were omitted from my discussion up to now. One of these, the brightest of them, is this waning gibbous moon, which we see here. A waning gibbous moon, remember, is a moon that is past full and so it rises after sunset, and at 9 p.m. we're still seeing it in the eastern sky, so we expected that. The moon happens to lie very close to the ecliptic right now. It could have deviated, remember, by as much as 5 degrees. We also have the next brightest object in the sky is the beautiful planet Jupiter. And we have not brought up planets. And once we allow that, we see that scattered along this ecliptic are a few others, non-star objects, Neptune, Uranus, and the asteroid Ceres. And if we look at this image over time, we would notice that, like the moon and the sun, the planets move as well, which means we're going to have to start next week by adding even more moving parts to our universe and enriching what we know and eventually leading us to much, much deeper understanding.